This hardware setup connects the Arduino board to both the ultrasonic distance sensor and an LED indicator. The LED's cathode is connected to the ground, and the anode is connected to the resistor. The resistor is connected to the D8 pin on the Arduino board. This allows the LED to turn on and off whenever it senses motion. For the ultrasonic distance sensor, there are 4 main pins: the ground, trig, echo, and VCC. Ground is connected to the Arduino's ground. VCC is connected to the Arduino's 5-volt pin, providing power to the sensor. The trig pin is connected to the D7 pin on the Arduino board, and the echo pin is connected to the D6 pin on the Arduino board. Finally, the Arduino board itself is connected to the computer by a USB cable, allowing the Arduino to send the signal to the computer.
The software is structured as a MATLAB class called ECE Distance GUI built using object-oriented programming in the app designer. Each button in the GUI is linked to a specific callback function that handles user actions. For example, connect button pushed initializes the Arduino and sensor objects, while start button pushed creates a timer that repeatedly calls the tick function to stream and plot data in real time. The app also includes helper functions like plot, calibration, compute errors, and reset live axes, which handle background tasks like generating calibration curves, performing polynomial error analysis, and managing the graphs dynamically. All user inputs like selecting a material or a polynomial degree automatically update the logic through these callbacks, making the interface user-driven and modular. This design keeps everything running smoothly without any manual code execution from the command window.
So the first step is to press connect, and the connection status pops up, indicating that the Arduino connected successfully, as you can see right here. Then you press the button start, and this is going to take raw live data from the ultrasonic sensor, and it also displays the raw data and calibrated data depending on the coefficients that were calculated, using our measured data points from 5 centimeters to 110 centimeters. Depending on the degree and the material that was chosen, different coefficients would be used to calibrate the data. Then you can press stop to stop collecting data points. Then you can press compute true error. Depending on the material that was used, it will show you the average true error, relative true error, and relative approximate error from degrees 1 to 2, and the average relative approximate error from degrees 2 to 3. This is also all graphed on the graph right here, this graph. Then you can press compute velocity. It takes the derivative of the position graph here, the first graph, and it changes it to the velocity graph. It also calculates the velocity from the forward, the average forward right here, and the central equations, and then it also takes the average of the overall velocity, which is present in the first graph. This graph changes to a velocity graph, which is the derivative of the original position graph, and then it tells you the average velocity here, right at the bottom. Last, we have our 2 buttons here, which are save data and load data. Save data lets you save the data that was collected, and load lets you load the data that you had previously collected prior to doing the experiment.